So I'm going to talk about what is weighted least square regression. You might have heard about what is the ordinary least square regression. This is different from the ordinary least square, commonly known as OLS regressions. So we'll see how it is different and in which all cases you need to use the weighted least square instead of ordinary least square. Well, weighted least square is popularly known as the WLS, and the ordinary least square is known as OLS. So the ordinary least square assumes that there is constant variance in the errors. The method of weighted least square can be used when ordinary least square assumption of constant variance in the error is violated. Okay, so this is the important point to remember. So you can use WLS in place of OLS when the constant variance assumption is violated. So you cannot use OLS if your error is not homoscedastic, right? In that scenario, you can use the WLS. So now it's clear where exactly what is the fundamental difference between OLS and WLS. Now we'll get into the deeper theory of the differences, and we'll understand how we can make the best use of WLS when we cannot use OLS. Okay. Now the scenario when the error term is not homoscedastic, where it doesn't have a constant variance, we call that as heteroscedasticity, right? So whenever we have the heteroscedasticity, we need to use WLS. Of course, there are other means of getting rid of heteroscedasticity and using homoscedasticity, but one of the way is using WLS instead of OLS. And the model that we're considering is this one, a simple linear regression model where y is the dependent variable, x is the independent variable, and epsilon is the error term, and beta is the set of parameters. Now let's get into a little bit of deeper mathematics. You may not be comfortable with the depth of mathematics involved while explaining the difference between OLS and WLS. I'll just give you a brief overview of how estimation is different in OLS than what we do in WLS. Okay, we all know that epsilon is the error term, and it is assumed to be having a multivariate normal distribution with a mean of 0 and a constant variance, right? Mean of 0 and variance is constant. Okay, now we have this the variance covariance matrix with us. Okay, and this relates to all the observations in your data sets. Now with this in mind, we define what is known as a weight of something. Okay, so weight of something or weight of an observation in your data point is defined like this. Weight is nothing but the reciprocal of its variance. Okay, now the reason we're talking about a particular observation is because each of these error term is associated with a single observation, right? And it differs, like you have error 1, error 2, and so on, right? So we defined weight 1 is 1 by sigma 1 square. Sigma is what we have defined here, right? This is sigma 2, and so on. So this is nothing but the variance of the error terms, right? The covariance, of course, are all 0 for the errors. Alright, so with this in mind, let's see the differences in the estimation of OLS and WLS. In WLS, in weighted least square, we try to estimate by minimizing the square of the errors, the sum of the square of the error. Okay, keeping in mind the weights we have defined, and I'll tell you what the logic behind it. Okay, I'll tell you the formula first, and then I'll talk about the logic behind it later on. Okay, so mathematically you can find the estimates of the WLS estimates by using this formula. Now if you remember what you have learned in OLS, we do not have the W terms in OLS, except except that it's exactly the same as OLS. In OLS, you find the beta parameters as, transpose of x multiplied to x, and then inverse of that, and then this multiplied to transpose x multiplied to y. Now this is how you find the estimates for um, ordinary least square. Okay, well, here we are simply adding one more term, which is the vector of uh, different weights. We defined the vector of weights in the previous slide, right? That's simply we are multiplying that here. Multiplying that with the x transpose and x. All right. So having this in mind, and with this this formula, the difference we know in terms of how the formula for calculating beta parameters is different than what you use in OLS. We'll see the intuition behind it. Why do we include a weight parameter here? Okay, the residual sum of square that we minimize is in OLS is nothing but the sum of the square of yi minus xi beta, right? There is a slight change here. We simply multiply the weight vector, and the rest of the the expression remains the same. It is the sum of the square of the error, which is nothing but yi minus xi beta square, except the fact that we are multiplying with a weight parameter or weight vector wi. Okay, why do we do so? Okay, now let me explain to you what heteroscedasticity is, where you have non-constant variance, right? You have some has high variance, some has low variance, and so on. Now this happens in areas where you have high variance of some observations and low variance for some of other observations. Now ideally, what do we want? We want less variance or constant variance. Okay, whatever variance we have, we should have same variance in place, right? So we want the the um, the weight that is given to each one of these observation in the estimation process should be weighted rather than equal weight, should be having different weight. Okay, so the one which has the higher variance should be given the lesser weight. Okay, high the variance, low is the weight. Okay, so that's the logic, because one that has high variance is most likely to be varied very high, so it's difficult to predict what exactly the actual value is, whereas variance observation having less variance in terms of observing it is most likely to be somewhere uh, near the mean, so we give more weight to that in the estimation process. But if it has high variance, it could be this value this big or this small. That's bad, because you will have your estimation process in that case will be erroneous, or it is not going to be very accurate if there is a high variation in the observations. In that case, we give less weight to such observation which has got high variance. So this will get less weight, whereas this will get a higher weight. Okay, so that's the idea here, and that's why we are in ordinary least square, irrespective of whether observation has high variance or low variance, or error term has high variance or low variance, you will get the exact same weight given to each observations in the estimation process. Whereas in OLS, the weights are given differently. So here the observation with small error variance has a large weight. If small error variance, so this has smaller error variance, right? Smaller one, and we have got higher weight. And the one has higher variance will get a smaller weight. And the information observation that has large error variance will get a smaller weight. Now the weights have to be known a priori, right? So that you can do the estimation. But not always you will get the weights, because when you measure an observation, you actually do not measure the variance many times. So in the real world, you have to find it in a way that is most approximate to the actual scenario. So let's see. So we'll understand how we measure the weight and how do we estimate by taking an example, and then it will be more clear. So we'll take an example. Here is the data gelton.txt. You can find it on net. It's a famous data set that has got same measurements, and we have got x variables and y variables. So what is x variable? It is the diameter of the p in inches of a parent plant. So we have the peanuts, right? So we have the diameter of the piece of a parent plant, and the progeny has also the seeds, right? So that diameter is taken as the dependent variable. So we're trying to find out how the progeny diameter depends on the parent diameter, right? So we're trying to basically estimate y, which is the diameter of the nut the seed from the progeny plant is related to diameter of the seed from the parent plant. So this is y, the diameter for progeny, and this is x, the diameter for the parent seed, and we have estimates alpha and beta. So that's exactly what we are trying to do here. Now remember one thing here, we have taken many seeds from each individual parent. So from each individual parent we have many progeny, right? So we have different diameters. So when you have different diameter, you can easily get the standard deviation or the variance of it, right? But that's not the luxury in each scenario or in each example. So in this example we have the standard deviation of the offsprings of the progeny, the seeds given to us. So the estimation process will be slightly easier in this case. Okay, so let's go ahead with the estimation. The standard deviation reflects the information in the process y. Now we need to remember that y, so we have y and x, right? So y and x, here we have the diameter. Okay, let's say diameter is 20 millimeter. Okay, here it is, let's say 19 millimeter. Okay, now this 20 meter has been an average of many seats, let's say 10 seats. Someone has 19, then 18, 17.5, 21, 21.5. So you take the average of that, because each parent has many offsprings, right? So you take the average of that, and that's exactly represents the y value. Hence, given that we have several observations, we can always find the standard deviation of that observation or the variance of that observations. So that we can use that as the weight. So that we have the standard deviation for the offsprings, right? And we can use that as the weight. So what weight is nothing but the reciprocal of the variance, right? So we can easily find the weight, and then we can use that in the ordinary least square. We have the formula. We saw that 3 slides back. So we can use that formula, which is nothing but x transpose, weighted weight matrix multiplied to x, whole inverse, and then you multiply it with another set of this expression and find out the beta values. And that's all. It's easy, right? But not always you will have this set of observation given to you. So experimentally this is possible, but many times you don't have that experimental data where you have several observations, so that you can go ahead with calculating the standard deviation and variance. So the idea is to give downweight the observation with large standard deviation. So we have the standard deviation for each observation for y value, and upweight the observation which has got small standard deviations, right? So logically that's what we need to do in weighted least square. That's what we also learned in the previous slide, that based on the standard deviation our weight will differ, and that is inversely proportional. That means the more variance you have, the less weight it gets in the estimation process. So when you use Iterative and we have this regression equation, you can use any software, R, SAS, SPSS. So this is the OLS, this is the WLS regression output, and this is the ordinary least square output. So we have used the same data and used different estimation process. So this is OLS, and the one above is the weighted least square. You can see that the difference in the estimates, right? Both in the intercept and slope groups. There is a significant difference in the slope coefficient at least. So intercept is not very different, but the slope coefficient has a difference. Hence, when you explain the marginal effect, that is going to be some change, right? Some difference. So here WLS is more appropriate because we have found out that variance of the error terms is not constant throughout. Hence, ordinary least square it's not appropriate because of the violation of the homoscedasticity assumption. When you do the plot by estimating, you find some difference. Okay, slight difference. You can see the two lines here. They're more or less overlapping, but there is some difference. Most of the times you will see that they will be very close. Okay, there won't be much of a difference, but it does make a difference when you explain it. So if you are doing a forecasting of something, that won't make much of a difference. But if you're trying to explain the marginal effect, then it does have a significant difference. For this example, the weights are known. As I have said, the weights are known, but this circumstance will not be there always. So how do you find the weights when the weights are not given explicitly? Well, you have I observations, which is an average of n observations. So the ith response of a data set is an average of n observations. So variance will be calculated very simply, right? Variance will be nothing but variance divided by ni, and the weight will be proportionate to that. So 1 by ni proportionate will be ni itself. So that will be the weight. If it is the total of ni observation, if the ith response is a total, it's just a sum of ni observations, then its variance will be simply the product of all the variances. Okay, here it was average, so we simply divided ni. Here it is the sum, so we just did the product of all the variances. Given the weight, product of the observation, number of observations, the variance, and the weighted is exactly the reciprocal, which is 1 by ni. So this is what you need to remember while aggregating the observations, right? So these are additional information. You can always read more about it, how you aggregate observation based on, like in our previous example, we saw it is an average of different observations. So the aggregation is average, but it will not be average all the time. It could be sum also. It could be some sort of different weighted average also. So how do you come up with weights when you have weighted average observations? Anyway, we are not going to deeper aspect of it. We'll keep it simple and go ahead. So now we have one example where you have the weights already given. We'll go ahead with another example where weights are not explicitly given to us. So when that is the case, we need to follow a few steps. Okay, before that, few observation about WLS. The weighted least square estimates of the coefficient will usually be same as the ordinary least square. I have already said that OLS estimates will most likely be same as WLS. So it doesn't help much in changing the forecast, whereas it helps a lot while explaining the marginal impact. In cases where there is a substantial difference in the OLS and WLS estimates, you should do a scrutiny, or should do a more thorough investigation of the estimation process, and you should do it more iteratively, so that the estimation, the coefficients will stabilize, and that's what we call as iteratively re-weighted least square. So there is large difference, that is a matter of worry, because that should not be a large difference between these two kinds of estimates. So in that case, you should iteratively estimates the WLS parameters, and there will be a time when it will stabilize very close to OLS. In some cases, the value of weights may be based on theory or prior research, and this is important. Many times you do research based on what has already been done in your given area. So someone might have taken weights for observations in your previous study. In that case, you can always go ahead with using the weights that the other researcher has used, but ensure that it is theoretically sound and it has been peer reviewed and published, so that you can always consider the data to be reliable. In design of experiments, when you have you're doing experiments through a proper design, and design of experiments is a well-known phenomenon in statistics. A large number of replicates weights can be estimated directly. So if in the scientific experiments you can always do more experiments to get more observations. So if you are doing experiments in botany, chemistry, physics, or engineering sciences like civil engineering, electrical engineering, mechanical engineering, you can always find multiple observations for the same observations, and then you can aggregate it by averaging it out, right? That luxury you have when you are doing scientific experiments. So you can always find the standard deviation, variance, and then use that as the weight. Okay, so it depends on the weight. So choosing the weights is the most trickiest things. And if you're not familiar with weight, it's always good to go ahead with the OLS instead of using wrong weights. So you have to be very careful while using the weight. We'll take another example where weight is not explicitly mentioned. Okay, in that case, how do we use WLS, right? So here is an example of a house price. So y, which is the target or dependent variable, which is the sale price of a home, and x1 and x2 are the independent variables, which is the square footage of home. And then there is another variable x2, which is also some sort of feature of the the house. Now using x1 and x2, we need to find out how they are related to the price of a home. So we use the ordinary least square, and we found out the estimates. We have the coefficient, standard deviation, t values, p values, and so on. When you plot the residuals, we found that it's not firstly, it's not random. Secondly, the error variance is different. Here it is less, but here it is lot more, right? So clearly there is a difference in the error variance, right? It's more conical in shape, and it seems that OLS doesn't work because the error variance seems to be non-constant. So how do we go ahead with estimating using OLS? There are 5 steps to be followed. So first, store the residuals and the fitted values from the ordinary least square. So start with OLS, the way we have done previous slide. Start with OLS. Do the estimation using ordinary least square and store the residuals in some variable. Okay. Calculate the absolute values of the ordinary least square residuals. Right. You can always calculate the absolute value. How do you do that? Just take the modulus, right? You can always find the absolute value. It may not be the negative values all the times, right? Because negative value doesn't mean anything. It's just the difference, right? So it has to be always a positive one. So take the modulus of all the residuals. Regress the absolute values of the OLS residuals versus the OLS fitted values. So what is fitted value? Your y hat is the fitted value from OLS, and your error terms are the absolute value of error term, by the way. Do not have to be negatives, right? Now you have error terms and you have fitted values of your dependent variable. In the third step, what do? You regress the absolute values of ordinary least square versus the OLS fitted values. So OLS fitted values is y hat, and this is your error terms. So you regress this as a dependent variable and this as independent variable. Okay, you do the regression. Okay, this with this. Okay, the error terms, absolute value of the error terms with the fitted value from the ordinary least square. You might wonder, why are we doing this? Well, we are doing this because we want to get more smoother values of the error terms. Okay, that's the idea. Other than that, there is no reason why we do it. Is to get smoother values, and this is what done in many other statistical techniques. So you can always ask your statistics teacher why we regress the fitted values many times. It is more or less to get smoother values. Okay, so this is more like an interpolation or extrapolation type. If you're familiar with these concepts, you would understand it very well. Okay, calculate weights equal to 1 by fit square. So whatever the fitted values are estimates of the errors. Now what you do is that once you regress, you store the fitted values from this regression. Now fitted values of regression will be again some sort of, okay, let's call that E dash, okay, and this is again estimate, so we'll use hat. So from this regression we'll get this error terms. This will be more smoother compared to what we have used here. Calculate the weights equal to 1 by fit. So this we considered as the standard deviation for each observation. We didn't have standard deviation in the initial data. So using this three steps, we calculate the standard deviation, and then we use that standard deviation to calculate the weight, and weight is nothing but 1 by the E hat dash square. Okay, so this is the weight, and this weight will be used for each observation. And once we have the weight, then it is very simple, right? We already know the formula in this in the slides earlier to this. We have written the formula. Use that WLS formula and find it out. You can always do the estimation through software. You do not have to do all these steps on your own, except the fact the first three steps are important. You have to do these first three steps on your own, and then the software itself will do it. And nowadays it's all automated. Now you don't have to do it on your own. You can use a WLS, a procedure or function in R or SPSS, and that will do all the steps. So the reason I explained all 5 steps is for your understanding of theory, so that you can always explain how WLS is different from the ordinary least square. Now we have followed the same steps that we explained in the previous slide, and we have a different set of estimates this time from WLS. Okay, so this is different. You can compare it with the ordinary least square estimate. When you plot it, you can see the values are a lot different. Now you have more or less constant variance. There is some sort of non-constant at the end, but then you can always try it out different weights to avoid that. But most part it is a constant variance, right? You can see it yourself, and you can compare this graph with your previous OLS graph, where the variance was non-constant in nature. Okay, so this is how you estimate, find out or estimate the OLS, the WS regression problem. There are certain points to remember while using WLS. The weighted regression is not an appropriate solution if the heteroscedasticity is caused by omitted variables. Many times, heteroscedasticity problem is there in your data because of omitted variable. That means you have missed out on an important variable. In that case, weighted least square is not a very suitable way of handling heteroscedasticity. There are other ways to handle it. Maybe you should go ahead and use the omitted variable, right? That's the best way. If that's not the case, then WLS is a good way of handling heteroscedasticity. Determining correct weight is a big challenge. Okay, if it is already given from an experiment, that's good. Otherwise, you have to follow the 3 steps I explained in the previous slides. The value based theory. I mean, when you are using literature, you are referring to some literature in your area of research. You can always take good weights already used by your previous researcher, and if it is a published work, it is always reliable to use the weight. So give some importance to literature in your area of research. Thank you so much, and if you haven't subscribed to our channel, please do subscribe. Thank you.